Log on, tune in, find out. Another good idea from Cambridge.
We're going to talk about Brill-Noether theory for vector bundles with fixed determinant.
Okay, so I am going to start by saying a few things about Brill-Noether theory for rank higher than 1 and without fixing the determinant. And then I'll talk about fixed determinant, because essentially the aim, at least for me, is to understand what happens when you don't fix the determinant, and we don't at the moment. So we had some expectations that came from studying the case of rank 1. It was very clear from the start that we would not be able to get the same type of results, because there were a lot of things that were not behaving the way we expecting. And the more we know about, the less we understand what the answer should be. So we hope that studying what happens with fixed determinant will tell us at least why some of the things that don't work the way one would expect initially go some other way. All right, so let me start, and I'm going to talk all the time about a genetic curve. So I am going to assume that C is a genetic curve of genus G, because we don't understand the genetic case, so if we want to go to special cases, that's going to be even worse. We define, as usual, the moduli space of vector bundles of rank R and degree D, which are stable. We denote it that way. And we consider then the Brill-Noether locus inside that, which I'm going to write as B, R, D, and K, as the set of vector bundles C, such that the rank is R, the degree is D, and also it has at least R plus sections. K, it's going to be our number of sections. And when we want to fix the determinant, we are going to consider, instead of this moduli space of degree D, the moduli space for a fixed determinant L. So if L is a line bundle, which we might say has degree D as well, we consider inside here the vector bundles which have determinant L. And the analogous locus would be the intersection of these two spaces, so it would be the BRLK. Set of E, again, with the determinant being K, L, and at least K sections. And these are not only sets, but are schemes. And one can give the scheme as, locally at least, a determinant of variety. The way we think of it is the following. If you take a vector bundle of any degree and you tensor positive degree, because we won't have any sections if the degree is negative, we take a divisor on the curve and we tensor with this divisor of sufficiently high degree, then we are going to have a vector bundle of high degree, right? And once the degree is sufficiently high, the number of sections is not a mystery. You just use Riemann rock and you find it. So if we take E of D for D of sufficiently high degree, we know that the H of E of D is, and we have a natural map to evaluating at the fibers, and the kernel is E, right? Now, all these spaces have the same dimension when E varies, D is fixed. And now we let E vary in the corresponding space. Then all these spaces will form a vector bundle over U of RD. And all these spaces are going to form a vector bundle over U of RD, right? So if we assume, for example, that we have a universal bundle on our moduli space, which does not exist globally, but locally does, we can think of this as the push forward of this universal bundle E on U of RD cross C. We take the push forward tensor with the pullback of that divisor, and that would give us a vector bundle with these fibers. And similarly, if we take E tensor P to that should be upper star OCD, that will give us a vector bundle with these fibers, and the kernel give us a vector bundle, let me call it F, whose fibers are what we want to have dimension at least k. So if we think of the locus where this map of vector bundle degenerates, we are going to have the BRDK that we want. All right? And we could do the same thing, instead of doing it over here, doing it with L, and we are going to have this other locus that we want. So locally, this is a determinantal variety, and for the determinantal varieties, we know that at every point, the dimension is at least what we would get by pulling back the conditions that we would have in the more generic determinantal variety of matrices. And this gives us an estimate for the dimension. So we expect that the dimension of BRDK is greater or equal than the estimate given because of being a determinantal variety. And if you try to compute what this number comes out to be, what you get is the following. That's the dimension of the moduli space minus H0 of E, H1 of E, where we are assuming that the H0 of E is K. Okay? And it's not only that the dimension is greater or equal. What we mean is that whenever we have a component, the dimension has to be at least that big. We can never have a component of smaller dimension. It may be well be the case that that number is positive and still the locus is empty. There is no guarantee that this is not going to happen. But whenever it is non-empty, any component has to be at least that big. All right? Now, it is not true that when the number is positive, the locus is non-empty. For example, you could have negative degree and have this number positive. And then, for trivial reasons, it's going to be empty. There are other cases in which it is not so trivial, but it still can be proved sometimes that the locus is empty even with positive expected dimension. If we do the same thing for L, we are constructing again a determinantal variety, now over a smaller set, the set of determinants with fixed, the set of vector bundles with fixed determinant L. So what we should get now as the estimate is greater or equal than the dimension of U of RL minus the same numbers. Okay. Now we are going to see that this second estimate, when the line bundle is sufficiently general, might be a good estimate if the degree is sufficiently high. If the line bundle is special, and special here means special in the classical sense, that H1 is different from 0, then that's not a very good estimate because we should have something substantially larger. And in fact, so large that the new estimates that we get by this, for this dimension are sometimes bigger than this number here. Okay? So when this happens, that will tell us one reason why this number cannot be equal to. because if we get an estimate here which is bigger than the estimate we had before, and this has to be contained there, then there is no way that we are going to have equal over there. All right? Before we go to the dimension, let's see what happens at the level of tangent spaces. So, and that was one of the ways in which things were proved. And maybe before I go on, I should say what happens in rank 1. So in rank 1, everything is nice. So R equals 1. We don't need to consider this second case because that would be nothing, right? If you fix the determinant, there is only one line bundle. So that's it. But if we don't fix the determinant, that estimate gives us equal. And what happens is on the generic curve, the B1dk, and people usually write it as W D, and now would be k minus 1, where the k minus 1 equals R. That's the classical notation. All right. These BDKs are non-empty if and only if that dimension, where did I write it? I am going to write this as rho because that's the classical name. The Brill-Noether number RDE, RDK. Okay, if and only if the rho 1D k is greater or equal than 0, it is irreducible for generic curve if and only if the rho is strictly positive, and moreover the singular locus of B1dk is precisely the B1dk plus 1. Okay, so everything is as nice as it can possibly be for the generic curve. For special curves, of course, this is not true, but that's not a drawback, it's probably an advantage because that's the only way we had so far of studying moduli spaces of curves. These curves that did not behave in the traditional way or in the expected way, they find nice subvarieties inside the moduli space of curves, and then you can study them and you can deduce nice things about the moduli space of curves. All right. Now, what happens for higher rank? Let's try to look first at the tangent space to the Brill-Noether locus. We first need the tangent space to the moduli space of vector bundles, and essentially that should parameterize the deformations of a vector bundle, so it should parameterize the H1 of E, right? E tensor E star. That should be identified to the tangent space at the point E to the U of RD. And if you want to be explicit about how to identify deformation with an element of H1 of E star, I forgot the star, E star tensor E, you can think of an element here as given, you can have your curve, which is a union of open sets, UI, and you want to give first order deformation of the E, so locally it's going to be something like E plus epsilon E, where the epsilon squared is 0, right? On each one of the UIs, and then you have to say how you glue them together. So you have to glue this on UI and on UJ, and that should be given by a matrix between that in UI and that in UJ. And the matrix is given by something like that. It should be the trivial deformation over E, right? Over when you forget the epsilon, so it should be something like this. And these phi ij are maps from E to E, and this gives you the element in H1 of E star tensor E. And now if you try to look at the deformations that also deform some sections, so you have a section S of E, if this is to deform, then it has to extend to a section of this deformation. So you have to give two components, one for E and then the other for epsilon E, and you are saying that this matrix transforms one of these into the other. So you have something like this. When you apply this to your S restricted to UI and something else that you need to have here locally, you should get the same thing over J. And this tells you that when you apply the phi ij to S, what you get is Sj minus Si. So essentially you are saying that the deformation acts on the section. So when you consider the H1 of E star tensor E, and you make it act on H0 of E, you end up with 0 in H1 of E, right? So you are looking at the kernel of the map from H1 of E tensor E star into the set of homomorphisms from H0 of E to H1 of E. And that would be the tangent space that we are looking for. The tangent space to be R, D, K, okay, at the point D. If we consider instead of this map, the dual of this map, the dual of this map is going to go from H0 of E tensor, the dual of that, which is H0 of K tensor E star, and the dual of the H1 is the H0 of K tensor E tensor E star, and that map is just a cut product map, which is usually called the Petri map. So the tangent space to the Brill-Noether locus is the orthogonal to the image of the Petri map. So the tangent space to Brill-Noether is the orthogonal to the image of the Petri map. And if we look at dimensions here, that was the tangent space to the moduli space, so the dimension of this vector space should be the dimension of the moduli space, right? And the dimension here, that's a tensor product, so it's the product of the dimension of the two spaces, H0 of E, H1E. The difference between the two is the expected dimension we have somewhere over here, which says that the Petri map is injective if and only if at this point the Brill-Noether locus is non-singular of the expected dimension. The Petri map is injective if and only if E is a non-singular point of BRDK of a component of dimension rho. And in particular, if the Petri map is not injective, as we knew from already in many cases for generic curves over 20 years ago, then that doesn't work. Okay? So now let's try to find some reasons why the Petri map is not injective by looking at what happens when we fix the determinant. And we might want to find out what does the tangent space look like when we fix L, right? And in order to do that, we first need to know what is the tangent space to the locus of vector bundles when the determinant is fixed L, so the moduli space of vector bundles of fixed determinant. And you need to remember for that that we can decompose the space of endomorphism of a vector bundle as a direct sum. So E tensor E star is in a natural way isomorphic to the trivial bundle O, direct sum the set of traceless endomorphisms. And the decomposition works that way. If you have an endomorphism phi from E to E, you can consider each trace that you can think of as a function. And if you take the endomorphism and you subtract the trace divided by the rank times the identity, you get a traceless endomorphism, right? We are assuming that the characteristic is 0, otherwise you might not be able to divide by R. And if you want to go the other way around, then you just consider the two inclusions. So if you have an F and psi, you send this pair to F identity plus psi. And then you can see that if you take the H1 of the E tensor E star, it's also going to decompose into the direct sum of the H1s of these two things. And if you look at the local representation that I gave at the beginning and you work with the basis, at some point you are going to see that this piece here is the one that fixes the determinant. And this piece here, as you might expect, corresponds to bearing the determinant because the H1 of O is the tangent space to the Jacobian. So that you expect that parameterizes the deformations of the determinant, but while these are the ones which don't deform the determinant. So we need to look at what happens at this stage. All right. Now let's look at the Petri map. And probably you are going to do just the case of rank 2, which is the one that we know more about. So let's look at what happens for rank 2 for the Petri map when we fix the determinant. Petri map for rank 2 fixing the determinant. And let me start with the case which is best known, which is canonical determinant. This case was studied first by Mukai and Feinberg and Bertram. And they came out with the right Petri map for this case. So what should be the right Petri map for this case? The first thing we need to remember is we are saying that the determinant is K. So we are rank 2, so the determinant is the second wedge power in this case. That's the canonical. And that allows us to identify the dual of E with some tensor of E. we have a natural map from E to the set of homomorphisms from E to K, which sends a vector E to the map which sends V to E wedge V, right? That happens to be an isomorphism. Now that's E star tensor K, which tells us that E star can be identified to E tensor K inverse. Okay? So when we are looking at the Petri map from A0V tensor A0 of K tensor E star to A0 of K tensor E tensor E star, and we make this identification of E star with E tensor K inverse, what we get here is just A0V tensor A0V, right? And what we get here is the K inverse is going to cancel with the K, so A0 of E tensor E. Alright? And this map is just the product map, so it's a very simple map. Now we want to project here to the H0 of the dual of that, and we said that the O corresponds to tensoring tensor K, right? The O corresponds to tensoring with the determinant. So when we have a vector bundle of rank 2, the E tensor E is isomorphic to the wedge 2 of E direct sum the symmetric 2 of E. Again in characteristic 0. In characteristic 2 I don't know what happens, I'm not sure. So what we have now as the map for the case of fixed determinant should be the composition of these into H0 of S2E. Alright? Now if we take this composition here, it is fairly clear that this map is not injective, because the second wedge power of H0V is going to map to 0. In particular, because the second wedge power maps to 0, we can factor the map here into a map through the second symmetric power. And the best we could hope for is that this map is injective. Okay? Now, how interesting is it that the map be injective? If we could say in some way that the map being injective gives us some other good property of this moduli space with fixed determinant canonical, then it's of some interest, right? And it's worth pursuing the case. And it does happen that this mapping injective gives us a good estimate, because we have another way of trying to estimate the dimension for determining the canonical. I defined at the very beginning, and that was in a board like this that I erased before, the Brill-Noether locus in general as a determinantal variety. Now let us see that when we fix the determinant being the canonical, that's again a determinantal variety, but for a skew symmetric form instead of the usual determinantal form. So we can do the following. I am going to take also a divisor D of high degree on C. And I am going to construct some spaces of bundles which don't depend on the bundle because the degree are sufficiently high or are supported on a finite number of points, and then it doesn't matter what the bundle is. And these are going to be the following. I am assuming an E of rank 2 and canonical determinant. And I take E of D, and E of D restricted to 2D. So the kernel of that is going to be E of negative D. And I am going to take as well E, which lies here, E sub D, and the same thing here. All right, so the bundle I want to consider is this one here. If I consider the space of sections where E varies, the D is fixed for once and for all, and the E varies among the vector bundles of rank 2 and canonical determinant, all these spaces form a vector bundle of rank 4 times the degree of D, right? Because when you take a vector bundle of rank 2 and you restrict to a point, you get something of rank 2, right? Locally a skyscraper sheaf of rank 2. And you have 2 times the degree of D points times 2 from the rank, it's 4 times D, right? So that's the E of D sub 2D form vector bundle over the U of 2K of rank 4 times the degree of D. And in this vector bundle, we can define a symplectic form in the following way. If you have 2 local sections here, you take the product of S and T to be the sum of the residues of S wedge T over each one of the points in D. S and T were locally sections of D, so S wedge T locally is a section of omega, right, the canonical. Then you take the residues and you take the sum at all the points. If you do that, we have here a subbundle, all right, and here we have another subbundle. That subbundle is going to be isotropic because we are considering sections which don't have any poles. If a section does not have any poles and you take the residue, you are going to get 0, right? So any 2 sections that don't have poles and you wedge them, you take the sum of the residues, you are going to get 0. So this is an isotropic subbundle of rank half because you had the degree instead D instead of twice D, right? If you look here, these are global sections of D. And there is a big theorem of complex analysis that says that if you add all the residues of a form over all the poles, you are going to get the sum to be 0. So that's another isotropic subbundle. And what you are interested in is the space of sections of E, which comes as the intersection of these 2. So the H0 of E comes as the intersection of 2 isotropic subbundles. And then there are some results about intersection of isotropic subbundles which tell you that the codimension should be this k plus 1 over 2. So from the estimate from symplectic forms, we get, and I shouldn't pull this up, right? We expect dimension of B to big K, little k, to be greater or equal the dimension of U of 2k minus k plus 1 choose 2. And this dimension is 3g minus 3. You probably heard that. Okay? So, in particular, this tells us that if the Petri map is injective, no component can be bigger than the estimate. The Petri map being injective tells us no component can be bigger than this number, the new Petri map, the one we define with the symmetric power. So, if the symmetric Petri map is injective, then any component of B to k is of the expected dimension g minus 3 minus k plus 1 choose 2. And probably the only any good piece of good news that we have so far in Brill-Noether theory is that the Petri map is injective for the generic curve. So we know that matches at least by now. So it is true that the Petri map is injective for the generic curve. We also have a good range in which we know that these loci are non-empty. So we also know, but not in every possible range. So not in all the good range. So this greater than 0 does not immediately imply that we know that the locus is non-empty, but we have a range in which we know that it is non-empty. So we know B to k non-empty for a good range of values of g and k. All right, so that's for canonical determinant. Now, what happens for other determinants? And there are some very recent results of Osserman which generalize the case of canonical determinant. And the generalization is fairly similar to the case of canonical determinant, at least for the case of at least one reason to be special for the determinant. Okay, so let me write this down. So the result says the following: if L is a line bundle and delta is an effective divisor, such that H1 of L of negative delta is greater than 0, so it's L of negative delta is special, and delta has been chosen as small as possible. So H1 of L of negative delta minus delta prime is equal to 0 if delta prime is contained in delta. Then the dimension of the 2LK at this point is at least the row of 2BK minus G plus K minus delta choose 2. And maybe I should say where this number comes from. If we look in terms of the Petri map, so the H0 V tensor, the H0 of K tensor E star to the H0 of K tensor E star, we can do something very similar to what we did for canonical determinant. It's still rank 2, but the determinant is not canonical. So here we would have the H0 V tensor, the H0 of K L inverse tensor E, right? And here we would have the H0 of K L inverse tensor E. And if we want fixed determinant, then we should map down to the symmetric power. And we should look at the composition of this map and see how big the kernel should be, right? Now we are saying that H1L negative delta is greater than 0, which means that the H0 of K L inverse of delta is positive. So we have a non-zero map from O to K L inverse delta, right? And then we can include in here H0 V tensor H0 of E of negative delta, right? And even smaller inside here, where the second map is a multiplication, so it's identity in the first component tensor with multiplication with this section. Inside here we get the second wedge power of H0 of E of negative delta. And as before, that should map to 0, right? So when we look at this number, that number here is the tangent space to the fixed determinant vector bundles. And that number here should come, hopefully, from that subspace inside here that maps to the kernel, right? Now, this does not seem to be right, because if you take a vector bundle of rank 2 and you impose vanishing at a point, you impose 2 conditions, not 1. And if delta is the degree of this delta, that should go down by 2 delta, not by delta. but it's somehow a little bit of a miracle. The fact that this map exists tells you that the number of conditions that this divisor imposes on the sections of the vector bundle is not given by twice the degree, but just once the degree. So that space here is the one that causes the trouble and requires this number to the image to have bigger dimension than expected, and therefore it should be there. And you can generalize the construction over there about determinant of varieties, and you find an estimate which is precisely that one by modifying slightly instead of mapping. So here instead of the 2D you did 2D plus delta, something like that, but you still have a symplectic form, you still have some isotropic subspaces, and you still have that the G of E is containing the intersection of these two isotropic subspaces. So the estimate, the new good estimate or better estimate for the dimension should be this number. All right. We don't know how good this number is. There are better estimates when the H1 is not just 1, so the only condition we're imposing here is greater than 0, but which means there exists a map like this. But if there is more than one map like this, then Osserman has a better estimate. And he also has some results for higher rank. I don't know if the results for higher rank are already public or not, but he's working on that. So at the moment, we have at least some good reasons why, when we don't fix the determinant, things don't behave in a nice way. We don't know if these are all the reasons or not, but at least there are some reasons there. And hopefully someday we will understand that. Now let me say what we can when we go to the other end. So that happens when the line bundles which give the determinant are very special. What happens if we take line bundles which are not very special, for example, of high degree? And in that case, we should expect good behavior. And it does happen. We have good behavior if we go up in the degrees. So we have the following. Assume again that this is a general curve, and L is a line bundle, general line bundle and C. And let's try to look at the Brill-Noether locus with fixed determinant. Then there exists one component of dimension 3g minus 3 minus h0v h1e if the degree of L is sufficiently large. And by sufficiently large, I mean the degree approximately to g minus 1. Now, you might say that 2g minus 1 is not very interesting. For the case of rank 1 is not, of course, right? Because then everything behaves regularly by Riemann-Roch. Now, for rank higher than 1, the interesting kind of interval when things might go wrong is between 0 and 2r times g minus 1, right? So that's approximately half of the interesting interval for vector bundles of rank 2. And of course this result is very weak. We only know the existence of one component of the right dimension, which does not exclude the existence of other components of the wrong dimension. Okay?
Sign
I have a precise estimate, yeah. I'll give you the precise estimate if you want it. You want it precise? Okay. So, if k is even, let me see, I have it here, right? K even, you need rho of 2lk greater than g minus 3, and for k 2k1 plus 1 odd, you need k1 plus 1 times k minus d plus 2g minus 1 to be less than g minus 1. Okay? I don't think I'm going to give the proof of that, but I just say a couple of words. The way this is proved is by the generation. So if you have a family, you have a family, let's say x over s, which is lots of curves, and over a point, so that's s, over a point your curve is singular, all right? You can make the construction of the Brill-Noether locus. Instead of doing it one curve at a time, you can do it globally over the family. Globally, I mean near the neighborhood of a vector bundle as usual, because you don't have these extensions, these Poincare bundles everywhere, but you do it globally, and again the condition on the codimension is going to hold. It's still a determinantal variety, and you are going to expect that if you denote by let's say curve B R L K, the Brill-Noether locus over S, the dimension should be greater or equal than the dimension of S plus the dimension of the U of R L K minus the H0 of V H1E. Because you start with something of this dimension and then you impose the vanishing conditions, right? So if you can find one particular curve and one stable vector bundle with that determinant at that many sections, and near that curve or near that vector bundle there aren't any more than the expected number. So if there exists a C sub 0 and E such that the B R D to B K of C sub 0 has dimension 3G minus 3 minus H0 VH1E near E, then this has to extend to the base of the family, because it has to be at least that big. It doesn't go up in dimension vertically, so it has to spread horizontally, right? And the secret is coming up with the right curve, right? And for non-singular curves, that's too hard. But there are some special curves in which we know what the vector bundles look like. The ones that we know where the vector bundles look like are usually the rational curves. These are very trivial. And then the elliptic curves, in which it is not trivial, but Atiyah did a lot of work on that, so we know them very well. And if we want to construct curves made of pieces like this. So if we construct a curve which has some elliptic curves and some rational curve joining them if need be, then we can say what the vector bundles look like on those curves. And we can say what the moduli space of vector bundles looks on these curves and what are the generic points and how we can deform one of these vector bundles. And we can construct one vector bundle which has the right number of sections and see what are the vector bundles lying around it which have that many sections. And after that, it's just a matter of patience or computation until you come up with the right numbers and the right examples. And I think I'm going to stop here.
Questions or comments? No, we thank Montserrat again.